Hello, and welcome to MultiFi's webinar, the Emerging 100 Gigabit Metro and Data Center Connectivity Opportunity, hosted by Gazettabyte. My name is Neil Nislusen. I'm the Vice President of Sales and Marketing at MultiFi, and with me is Roy Rubenstein, the editor of Gazettabyte. Roy?
Thank you, Neil. My name is Roy Rubenstein. I'm the editor of the online publication Gazettabyte, and I too would like to welcome you to this webinar. What's shown on slide 2 is a comparison between the 40 gig optical transport market and the emerging 100 gig one. In the case of 40 gig, a variety of technologies have been developed, starting with the simpler optical duo-binary, moving to the more complex phase shift keying schemes, and taking that one step further with coherent detection based on polarization multiplexing, quadrature phase shift keying. What this has meant for the industry is that as far as component makers and system vendors were concerned, they had to decide at what point to enter the market and with what technology to pursue. In the case of the operators, they too had to decide which of these technologies was best suited for their fiber plant. And at the same time, in the case of early adopter operators, they may have adopted the first technology that became available, only to rip it out and subsequently replace it with a more complex scheme for 40 gig, simply because of its enhanced performance was better suited to their fiber plant. In the case of 100 gig, the decision has been made to do this differently, and partly it is making good use of the experience that has been built up in developing the 40 gig marketplace. So the Optical Internetworking Forum, the OIF, made up of carriers, system vendors, and component makers, have chosen to alight on polarization multiplexing QPSK. But as the 100 gig marketplace starts to evolve, the question arises, is that one modulation scheme most suited to these various applications, or is there a place for a second scheme based on direct detection? So having posed the question, it is interesting to talk to the market research firms to see what they make of the emerging 100 gigabit direct detection marketplace. And here the views are mixed. So in the case of Ovum, they have just forecast the 100 gig direct detection marketplace. And what they are saying is this doesn't clearly include 100 gig coherent, and it doesn't include the IEEE 100 gigabit Ethernet schemes. And by 2015, Ovum forecasts that this will be quite a sizable market of the order of $250 million. They also do not rule out that this is a conservative forecast. In other words, it could be even greater. But their key point is that this is a marketplace and it will be the order of a third of the total 100 gigabit DWDM marketplace by 2015. Talking to Light Counting, and their view is different. They still have reservations about 100 gig direct detection, and I'll touch on these reservations in the next slide. What they're saying is, as far as their existing forecast is concerned, that goes out to 2014, that is made up solely of 100 gigabit coherent detection modules. But they also point out that they are working on their latest 100 gigabit forecast. They are looking at the 100 gigabit direct detection marketplace, and they will forecast accordingly based on the findings of their research. So in summary, there are very sound reasons why the industry has alighted on one modulation scheme for 100 gig. 100 gig coherent detection does have superior optical transmission performance compared to the other schemes mentioned. It's terms of its spans that it can achieve, but also how it handles the various dispersive effects of fiber. It also brings industry standardization that was clearly lacking in the case of 40 gig, such that all the vendors and component makers involved can invest their R&D dollars pursuing one scheme, and as a result of which hopefully build scale and lead to a more aggressive cost reduction curve. But at the same time, all of this enhanced performance comes at a cost. coherent detection is relatively complex. It has more componentry that results in a higher power consumptions, and it has an associated cost. And then the question is that the sort of solution that makes most sense for the more cost-sensitive markets such as the metro marketplace, or for relatively short links but which are above the distances being discussed by the IEEE? But then the other question is, even if there is a market opportunity for 100 gig direct detection, there are issues there, and this comes back to some of the reservations of light counting. So will operators back a second transmission scheme when they were the most vocal in making sure that the industry pursued one? Also, is there any consensus here as to how best to implement 100 gig direct detection? There certainly is in terms of 100 gig coherent. And will there be a standard? Operators like standards, yet at the same time it can be argued that the 100 gig coherent is not necessarily an official standard as in implemented by the IEEE or the ITU, but there is a structure here put in place by the OAF. And then one other point, even if operators who are keen on standards perhaps are less interested in this technology, at least to start with, there is another ingredient here, that it won't just be operators that might use this technology. There are also players like internet giants that have their own networks, and they may very much value this approach that offers them a much cheaper alternative and which does the job. And then the last question is, what about the merits of 100 gig direct detection? Can these be quantified so that people know what sort of spans can it address and what is its relative cost compared to, say, 100 gig coherent detection transponder? So it is these issues and these questions that will now be addressed as I hand back to Neil from Multify.
Well, thank you, Roy. Once again, my name is Neil Neslusin. I'm the Vice President of Sales and Marketing over at Multify. Multify is an Israeli fabless semiconductor company that is providing DSP-based integrated circuits for high-speed communications. Simply put, we're building 40 gig and 100 gig CMOS PHY chips, or SerDes devices, for both direct detect and coherent applications. In this webinar, we're going to be focusing on our direct detect applications. Our market focus is enabling optical transmission between data centers and for metro and regional networks. And the premise of this presentation is that there exists a 100 gig transport opportunity that is not being well addressed by the coherent solutions of today or the IEEE enterprise solutions of today. We hope in this presentation to address this market opportunity. And the market can be characterized as the metro reach, very low power and cost as compared to long-haul coherent, pluggable optics, which is becoming much, much more important for all kinds of systems vendors, and perhaps most important, providing an evolutionary upgrade path on current topologies. I'm a big believer in looking back at history to try and learn from history to figure out what's going to happen in the future. So let's go back and look at year 2000 or thereabouts and 10 gig technology when it was rolling out. And let's think about our internet use back then in year 2000. Many of us had cell phones. By today's standards, they were relatively simple, just a simple GSM handset. We did some amount of purchasing of goods, merchandising on the internet, but not a whole lot. And there was nothing like video streaming today. And forget about Facebook, there was nothing like that back then either. The result was the internet experience was relatively simple by today's standards. We thought it was great back then, but big things were coming in the next 10 years. So how did this affect the network back then? Well, we only needed to really store data in one or two spots per data instantiation on the internet. So there was a centralized storage of content. Every time you wanted to access something, you went through the internet to get to where it was. And anybody else throughout the world who wanted to access that same data probably went to the same spot. The result was the long-haul network got stressed. And 10 gig got first deployed in the long-haul and ultra-long haul. We were not stressing the metro at the same level. So consequently, the metro got built out for 10 gig probably about 5 years later. It depends on where you were in the world and which network you were on. But the two spaces, the long-haul and ultra-long haul space and the metro, definitely grew differently and in different times. All right, now perhaps the most important slide. Let's think about how our internet use in 2011 compares to 2000 and how the network as a result is going to change to service that use. First of all, our phone is just bigger in every way than in 2000. Many of you have 3G phones, maybe moving to 4G depending on who your carrier is. And you can do a lot of stuff on your phones these days. It's getting to the point where some people are thinking maybe they can throw away their PC and just use their phone. You're buying a lot more stuff on the internet. A lot of people buy a lot of their clothes, a lot of their electronics on the internet. So the internet merchandising has gone up tremendously. If you've got teenagers like I do, you know that they play these role-playing games and stuff on the web that 1,000 people play with them simultaneously, and they're also chatting with 8 or 10 of their friends while they're doing it. And finally, video streaming is really the thing that's making the internet change fundamentally. The whole point here is that your internet experience is much more complex and sophisticated in 2011 as compared to 2000. Now, how does this affect the network? Well, the most important thing is we're now moving to what's called a content distributed network. And simply put, that means that the stuff that you want to access on the internet is no longer centrally located, but rather spread among big metro areas and many, many different locations. So the data centers, as you see in the picture below, the data centers and the internet giants' optical networks are really being built out in this extended metro and edge space. Now, what does that mean for the long haul in the metro? Well, first of all, we don't dispute the 100 gig is going to get deployed in the long haul and the ultra long haul. It's definitely going to grow. There's no doubt about that. But in order for us to preserve this internet experience that we've all come used to, we need the metro to grow concurrently. As a consequence, unlike the last big build-out in the previous decade, when the metro got built out for 10 gig, a good 5 years after the long haul, we argue that the metro is going to be built out at the same time as the long haul. Thus, the need for an acceptable 100 gig transponder for the metro. Okay, let's think about how the network operators are going to build these next generation metro and extended reach data center networks. First of all, as we mentioned on the previous page, there's going to be a very, very high bandwidth of metro connectivity in these networks. The data centers that they're connecting together, they're very, very large, tens of thousands of servers to hundreds of thousands of servers in each building. And in fact, the logical data center might even be bigger than that, and they may be in separate buildings, and those buildings may not be co-located in the same space. So the data centers, in many cases, are going to be distributed around a big metro ring. The result is you're going to have a lot of add-drop connections and high density of inter-data center connections between these buildings. Now, with regards to interoperating with existing networks, don't forget we're talking about a network that's being built in the metropolitan region. It costs a lot of money to lay new fiber, especially in and around a city. So there's a big desire to make use of the current network, make use of that brownfield network. And they want to do it without re-engineering the entire network. And this is important because this is where the carrier makes money. This is where the network operator is going to make its money. All the money they invested over the past 10 years needs to be applied in this new network paradigm in order for them to be profitable. The performance metrics that we're suggesting, well, we suggest two. There's sort of the metro/regional space, which we believe is up to about 800 kilometers of reach in a traditional network. And then there's the extended reach data center network, which is about 80 to 120 kilometers of reach with no regeneration points in between, no optical amplification points in between, point to point, as they say. Okay, cost and power. Well, here's a shocker. The network operators want it to be low cost and low power. Well, that's well and good. Everybody wants low cost and low power, but think about where this is being deployed. In the metro, where electricity costs a lot more, where the floor space costs a lot more. So the cost of the solution has got to be low, and it's going to be measured against 10 gig costs. Secondly, the power has got to be very low. It's got to be on the same on the order of the same power per bandwidth as 10 gig. And finally, it's got to be a pluggable solution. As I say, Datacom or IT hardware has slowly encroached into where telecom hardware has traditionally been deployed. And one of the outgrowths of that is the telecom operators have sort of fallen in love with pluggable optics. They're a lot easier to fix, obviously. If you got a problem in the network, you pull one optics module out, you shove a new one in. So pluggable optics, the desire for them is not going away, it's just getting stronger. Okay, now let's talk about the challenge as we see it based on what we talked about in the previous pages. When we talk about the modules being brought to bear in the 100 gig space, we feel that the up to 40 kilometer space, what we define as the short reach, is being well served by the IEEE modules. And the long haul space, somewhere over 1,000 kilometers, is being well served by the OAF defined 100 gig coherent modules. It's this space in between, 80 kilometers to about 1,000 kilometers, give or take 10% on either side, that we call the metro and extended reach data center space that is not well defined. Well, what's the solution for this segment? We'd like to describe that solution in the next few pages. But before we describe the solution, we'd like to talk about the market. A good question would be, Meltify is telling us this, but what does the rest of the market say? Well, you can see two things there. One from an ADVA release, where they're doing a successful trial of a direct detect 100 gig solution with a tier 1 European carrier, and a nice quote there from Christoph Glingener, who's the CTO of ADVA. And also, secondly, you can see the quote from Infonetics that they did in a report last year. In both cases, they're pretty much saying exactly what we're talking about, where there's a space between 80 kilometers and anywhere as high as 1,000 kilometers that's not well served by what's defined out there. The other thing we can say is in our meetings with some potential customers or customers, we've identified what we describe as an internet giant who is now firmly committed to an 80 kilometer pluggable solution. Well, if it's 80 kilometers and pluggable, we know it's not coherent. Okay, let's think about the technology enablers that exist today that allow us to bring this solution to the marketplace. First of all, when 40 gig came out way back when, 0.13 micron CMOS was mainstream. It was a great technology. You could build some big circuits, but you could not build the DSP needed for this application. The second thing is the 0.13 micron CMOS did not support the edge rates needed for 40 gig PHYs. Indeed, the first CMOS 10 gig PHYs were just coming out at that time. Well, when 100 gig came out in the past year or so, now we have 65 and 40 nanometer CMOS. They're here. And they certainly support the edge rates needed for 100 gig PHYs. They also support the gate counts needed for high performance DSP designs. And finally, they support the high-speed A to D circuitry needed for this solution. Now, all the work has not only been done by the CMOS guys, the optoelectronics companies have done their work as well. They've come out with next-generation integrated PIC technologies, especially at 10 gig, that have really increased the integration in these modules and significantly dropped prices. These two things have really allowed this solution that we're going to describe in the next page to come to market. Okay, so our solution is the Multify MP1100Q receiver chip. The resultant module that you'd build with this device is about 30% of the BOM cost of competing 100 gig coherent modules. And that BOM cost, incidentally, is tied to the continued reduction in the cost of 10 gig electro-optics. Yes, we use 10 gig, not 28 gig electro-optics in this solution. Will also be about 30% of the power dissipation of these 100 gig coherent modules. These two things allow us to fit inside a CFP, which will continue to drive the cost down of this solution. We sort of have two application spaces for this device. One is 80 kilometers of 100 gig transport on an unrepeated link with no penalty. That's sort of the extended reach data center connection that we were talking about. And the other one is 800 kilometers of 100 gig transport on a normally amplified and dispersion compensated network with no penalty. That's sort of the extended metro or regional reach some would call. Now, an important aspect of this solution is it's easily usable in existing brownfield networks. There's no re-engineering needed. There's no quieting of neighboring lambdas with this solution. And the spectral efficiency, while it's not at the coherent rate, is still pretty darn good. It's 1 bit per hertz, or as we like to say, 100 gig on 100 gigahertz. Here we have our MP1100Q inside a module that's on an example application of a system. The gray box to the right is a 100 gig line card, let's say, with a 100 gig direct detect CFP module on it, connected by COWI or OTL 4.10 to a 100 gig framer MAC and then an NPU or switch. The point there is we're not proposing a different interface. We're using all the standard interfaces normally found with these modules. Now, if you blow the module up, you see the guts of it, which is pretty much a 10 to 4 MUX IC, followed by 4 10 gig EMLs. In the receive direction, we've got 4 10 gig pins or APDs with 4 10 gig TIAs, and then feeding into the MP1100Q through the A to D, through the very important MLSE engine, which is our DSP, and then through the DMUX. Now, the DSP MLSE is absolutely the key to the solution, both extending the reach of the application and also allowing the use of 10 gig optics. We support 2 encoding schemes with this device, the MP1100Q. One is on-off keying and the other is optical dual binary. They can be realized in the same basic application space with a couple of caveats that I'll mention at the end of the slide. The application space, we've mentioned it previously, the 80 to 120 kilometer point-to-point network, and the sort of up to 800 kilometers or so optically amplified WDM network. From a cost perspective, on-off keying is a little cheaper than optical dual binary, with on-off keying being about 30% of the BOM cost of a 100 gig coherent module, and optical dual binary being about 40% of the BOM cost of a 100 gig coherent module. The power dissipation is also much lower, with on-off keying being about 30% of the projected power of a 100 gig coherent module, and optical dual binary being about 35% of the projected power of a 100 gig coherent module. The form factor, we're very, very confident the on-off keying solution can be realized inside a CFP. The optical dual binary solution, definitely in an MSA. There are some next generation subcomponents that we're looking at that are a little smaller that we think will allow us to realize a CFP footprint as well. Now, the difference in performance is, first of all, the ODB will offer a measure of increased spectral efficiency if the optical dual binary module is realized in a specific way. And you can also operate the ODB in a lower OSNR environment. So if you've got an optically amplified WDM network where you're going through a bunch of ROADM hops, you may want to choose ODB. ODB could be the solution for you depending on what the network is that you're trying to run. Okay, so here's a picture of our MultiPhy product line. Across the top of the direct detect devices, and of course the MP1100Q on the right hand side is the device that we've been focusing on in this presentation. It is a direct detect MLSE receiver. It does have a sister chip, the MP1040D, which is a 40 gig device, pretty much the same device, just targeted at 40 gig, and it's focused on both DQPSK and optical dual binary solutions. Both of those devices are available in mid-2011. In addition, we're also working on our coherent detection devices. They will be focused on the metro, and they are called the MP2040C and the MP2100C. And we'd love to talk to anybody who wants to talk about these devices at OFC. We're going to be at OFC, although we don't have a booth. If you do want to get in contact with us, please email me, Neil, N-E-A-L, at multi-phi.com, or you can call me at +1 978 302 5700. Again, we're prepared to talk in great deal about the MP1100Q and MP1040D direct detect devices, which are signed off to fab and available mid-2011, and also our metro coherent devices, which are in design today. So in summary, we believe there is a Metro Reach 100 gig marketplace that is not well served by the solutions that are available today. We believe the growing content delivery network will rapidly grow the 100 gig Metro marketplace. Our DSP-enabled direct-to-text solution, driven by the MP1100Q, is being brought to the market now, and it will give you a module with the following characteristics: 30% of the power of coherent, 30% of the cost of coherent, easily deployable in existing 10 gig networks without re-engineering, and finally, a pluggable solution. We look forward to your inquiries and ask you to come see us at OFC. I want to thank you very much for attending this webinar, and also thank Roy Rubenstein and Gazettabyte for the forum, and we look forward to talking to you very, very soon. Thank you very much.